Hello, my name is Svetoslav and I'll be presenting the paper with the very long name Annotations for Alloy, Automated Incremental Analysis using Domain-Specific Solvers. My co-authors are Serfras Khurshid and Dwayne Perry, all from UT Austin. Before I dive into the paper, I need to cover some background knowledge. First, I'm going to start with Alloy. Alloy is a declarative modeling language based on first-order logic with sets and relations. It's been developed by Daniel Jackson from MIT and his team. Alloy is analyzed by the fully automatic Alloy analyzer, which, given an Alloy problem, translates it into a propositional formula, which is then analyzed by an off-the-shelf set solver. The solver is trying to find a satisfying assignment for the formula. Alloy is a popular tool. It's been used for finding problems in semantic models, algorithms, modeling software architectures, generating tests, and so on. So here is an example of an Alloy model. Here's an example of an Alloy model. It's a binary search tree which has nodes, and we define all the entities in the model, and then we define some predicates which are describing how the structure behaves. I will cover the model in a bit more detail. First, we declare the module in the very first line, which is we're saying, oh, this is a binary search tree. After that, we're defining the nodes in the tree. We're defining the signature of the node and what the node contains. So every node has at most one left child. Every node has at most one right child. Every node has at most one parent. The root has no parents, and has a key, which is an integer. A binary search tree has a root, which is a 1 or 0 nodes, which if you have an empty tree, you have no root, and size. So now we defined all the entities in our model, and we need to describe how they are related to each other. If you look at this example, this is basically the predicate, which takes as an argument the binary search tree, and what it says is that for every node reachable starting from the root and following the left and right relations 0 or more times, the following holds. And the following is for every node following the left and right relations in reverse order gives it at most one node, and every node if you start from every node and perform if you follow the left and right relations 1 or more times, you cannot reach to the same node, which means that you cannot make a loop, and the left and the right children are disjoint. We are not showing the predicates, some other predicates, to save some space. We are only showing the binary search tree predicate, which basically states that the binary search tree should be acyclic. It should satisfy the parent relation, it should satisfy the search relation, and the size relations. So the parent relations pretty much is, the parent pointer is implemented correctly, and the search is that the keys in the tree are ordered correctly, and the size is that the size of the binary search tree is equal to the number of nodes in the tree. Once we defined all the predicates, we are asking from Alloy to solve the problem. We're saying run binary search tree for exactly one binary search tree and 3 nodes, which means we're asking, hey Alloy, given this model, can you find a binary search tree that has 3 nodes? And what Alloy does is performing an exhaustive search within the bounds we provided. And if it finds a solution within these bounds, it means that it doesn't mean that this solution will be valid for if you increase the bounds, or the inverse. If you don't find a solution for small bounds, it doesn't mean that it doesn't exist for larger bounds. Therefore, if you increase the bounds of the analysis, this gives more confidence in the end results. Which means that the goal is how do you increase the speed of Alloy such that you can reach larger bounds and be more confident in the results. I need to provide some more background also for declarative slicing, which is work done by Uzunkova from UT Austin. The basic idea there is taking give an Alloy model, divide it into 2 pieces, solve the first, find a solution for the first subproblem and then extend it to a solution for the entire problem. In more detail, the algorithm takes an alloy model, translates the model into its canonical form, which is a conjunction of predicates, pretty much this and this and this and this, and then selects a slicing criteria. Slicing criteria is just a subset of the relations in the model, and it says all the predicates that contain the relations in the slicing criteria go into the base slice, and everything else goes into derived slice. And then the goal is solving the base slice, finding a solution for the base slice, and then using this as a partial solution to when you solve the derived slice. So basically extending a solution for the base as for one subproblem to be a solution for the entire problem. Without going into too much detail, it's important to mention that there are many different slicing criteria in which you can partition the model, and they are ordered under set containment. So if you create, they are organized into a joint semi-lattice. Here is a graph of it. And then the question is which slicing criteria to use, which one will give the best speed up. The way declarative slicing does that, it's all the possible slicing criteria are tried for a very small scope, and the one that is fastest is the one that we high probably will yield the fastest results, and this is the one that it's used. So now that we covered the background, we can dive into our approach. Our paper makes the following contributions. We're performing incremental analysis with parallel reasoning about independent subproblems. We are integrating domain-specific solvers in Alloy via annotations. We have added dedicated string and integer solvers. We have implemented our approach and evaluated it on non-trivial subjects. So our approach is based on two key observations. One of them is that an alloy problem can be decomposed into many subproblems which can potentially be solved in parallel. And also, during this incremental analysis, we may be able to exploit some domain-specific solvers which are tailored for specific data types. They use special representations. They are much more efficient in their target domain. So there are two limitations of declarative slicing. It's partitioning the problem only into two subproblems, a base and a derived slice. And these two subproblems are solved sequentially. So the base is solved first, and then the derived slice is solved after that. In our approach, we're applying the recursively declarative slicing, and we are partitioning the problem into multiple subproblems, and we try to solve potentially independent subproblems in parallel. In our approach, we're using all the possible slicing criteria instead of only one of them, and in order to do that, we need to order them. So we need to order the way the slicing criteria in the order in which we want to apply them. How we do that? If you remember the joint semi-lattice of the possible slicing criteria, we start from that. And for every possible slicing criteria, we're creating a graph pretty much, and for every slicing criteria, we are adding a vertex, and we're adding an edge from a slicing criteria A to a slicing criteria B if B is the smallest slicing criteria that contains A. Given this graph, we're just performing a topological ordering of the nodes in the graph, and this gives us the order in which the slicing criteria order in which we want to proceed. In more detail, so once we solved the problem of ordering the slicing criteria, we can start solving the model. The way we do it is we partition the problem. We take the first slicing criteria, we partition the model into a base and derived slice, and then we solve the base slice, which is a subproblem. Assume that we successfully solve this. Then we partition the problem using the second slicing criteria, and Before trying to solve the base slice in the second step, we're taking the partial solution from step 1 and we are setting this partial solution to the current problem we're solving, and we're trying to solve it. This is repeated until either the problem is inconsistent or we just found the problem for the entire, we found a solution for the entire problem. It's important to note that it's possible a partial solution for a previous subproblem may not be extended to a solution for the current subproblem, because we added some additional constraints in the current iteration that so basically the relations were under constraint in the previous subproblem, and now they are more constrained. In such case, we backtrack to the previous subproblem, we find another solution for the previous subproblem, and then we come back to the current iteration and we try to find a solution. If none of the solutions for the previous subproblem can be extended to a solution for the current subproblem, we are backtracking before the current subproblem and apply the same search. If no solution for the very first subproblem can be extended to a solution for the entire model, then we're declaring the model is inconsistent and there is nothing else to do. It's important to mention that a sequence of slicing criteria in the topologically sorted list of slicing criteria, they may share no common relations, which means that they are independent, which means that we need to solve them in parallel, and we do so. Also, it's possible that a sequence of the a subsequence of the slicing criteria, they may share common relations, but they may not add additional constraints on these relations. So in this case, these subproblems may be parallel, and the way we figure out if they're really parallel is we are solving them in parallel for a very small scope, and we're trying to see if they generate a non-conflicting solution, then it means that they're really parallel. And in this case, we're solving these subproblems in parallel using the current scope, the normal scope. So the use of domain-specific solvers was also recognized by Uzunko from UT. But in his work, he doesn't. There are 3 limitations in his work that we think we can do better. One of them is his work doesn't define a mechanism of adding solvers to alloy, and we define such. We also define a mechanism to determine when to use a given domain-specific solver. This is something that Uzunko's work is lacking. And we're also adding a dedicated string solver, and Uzunko's work added only an integer one. The way we introduce, we introduce annotations that define data types, operations over these data types, and bindings from data types to domain-specific solvers. And we're using that for integrating domain-specific solvers. In more detail, we're adding the data type annotation, which can be placed only on an alloy signature, and it also it's pretty much mapping alloy signature to a domain-specific data type. So assume that you have you define your own custom integer data type, or node. If you look at if you remember the binary search tree example, if you want to use the signature of the nodes as a specific data type, you can put this data type annotation on it, and it takes one attribute, which is solver, and it means for this data type, this is the solver that you want to use. We're also adding another annotation, which is operation, and it can be placed only on an alloy predicate. And it's a mapping from an alloy predicate to a domain-specific operation. So basically what it says is this alloy predicate has to be translated to this domain-specific operation. And here's one example of how this works. We defined, so this is how we integrate actually an integer solver in alloy. We define a module with an integer, module is just an alloy file. And we define a signature integer, which is actually wrapping around the built-in integer type, and it has an annotation data type. It has the solver attribute is set to integer solver. What we're saying here is this signature is a new data type, and here is the solver for it. Below, we are defining the less than operation on integers. We define an alloy integer predicate, an alloy predicate, which is named integer less than, and it takes to integer, and it's just doing the less than comparison. And it has an annotation operation, which is mapped to the less than domain specific operation. What we're saying here is this alloy predicate has to be mapped. It has to be translated to this domain-specific operation during the when you translate an alloy problem to a domain-specific problem, and vice versa. So in our approach, we are using the metadata that we introduced via annotations to determine when to use a dedicated solver. And the way this is done is pretty much very straightforward. If all the variables in the current subproblem we're trying to analyze are of the same type, and this type has a data type annotation, we're saying, okay, everything at this point is of the same data type, and if this data type has to be analyzed by this domain-specific solver, so we're just giving the problem to the solver, and it solves it for us. If all three variables are from different data types, there is no way to use the domain-specific solver, and what we do is just we fall back to SAT and do the standard alloy analysis. Without going into too much details, but we're using the operation annotation when you do translation from alloy to domain-specific solvers, and so for example, if you see the integer less than operation, you know that when you do the translation, you need to use some other domain-specific, operation to perform semantically the same action. We also integrated integer solver in Alloy, and string and integer solver, but actually we used already implemented integer solver, which we kind of wrapped around some Java code, but for string solver, we had to implement our own because the problems we're tackling were multi-variable problems, and they were not supported by the off-the-shelf string solvers. We integrated an integer and a string solver into Alloy, and the way you integrate the solver is just write an Alloy model file, which is defining the signature with an annotation which solver to use for this signature, for this data type. Pretty much declaring the data type and declaring the operations, which is declaring the Alloy predicates and mapping these predicates to the domain-specific operations. We've evaluated our approach on several data structure models with integer and string data and peer-to-peer protocol from the standard Alloy distributions. And for small bounds, our approach actually is comparable to the standard analyzer, but as bounds grow, the gains of using our technique become more significant. And if you look at the maximum bounds reachable by the standard analyzer, so maximum bounds are the bounds where either the standard analyzer runs out of memory or it doesn't find a solution in 30 minutes. So for search bounds, actually our approach is about two orders of magnitude faster than the standard Alloy analyzer. So here's some related work. The first bullet is some work on Alloy. The second bullet is the work on declarative slicing. Then follows a reference to our previous work in which we introduced annotations which were specifying the order of solving of predicates and which solver to use for each predicate, but it was more of explicit partitioning of the problem into subproblems rather than, and our current work is actually relying on automatic partitioning, and the metadata introduced by annotations is more focusing on mapping from Alloy semantics to domain-specific semantics, and follows a reference to Uzunkova's work on test generation for product lines using the declarative slicing technique. And so lastly, this paper presents a way of extending Alloy's semantic model, adding additional actions, extending Alloy's semantics to support actions. In conclusion, we increased the speed of the Alloy analyzer by performing incremental analysis using domain-specific solvers. We introduced annotations for the defined data types, operations on these data types, and mappings from data types to domain-specific solvers. Our technique automatically partitions the problem into subproblems, which then are opportunistically solved in parallel if they are indeed parallel, and we integrate integer and string solvers in Alloy. We apologize for not being able to attend in person, but due to some financial reasons we cannot be present, but we'll be happy to reply and to answer any of your questions over email. Just feel free to send us an email and we'll try to get to you as quickly as possible. Thank you.